Welcome to the Sustainable Building Design Seminar, sponsored by Weyerhaeuser. I'm Brandon Ross, the Cottingham Associate Professor of Civil Engineering, and today we're welcoming a friend of mine, and actually an old colleague of mine, coming to us all the way from Idaho Falls, Idaho. So Justin Judy is our speaker. He's a professional engineer, and he's also has many different LEED certifications from help me out, Mick, leadership in energy and environmental design. Yep. And he's a mechanical engineer who designs HVAC systems and mechanical systems for buildings. And so one thing maybe he'll talk about, but I might just say about why this is really important, is the operational energy that it takes to turn the lights on and to keep our buildings hot and cool is one of the biggest factors impacting energy use and sustainability. So any seminar would be incomplete without having a mechanical engineer talking to us about building systems. So Justin is the president of Engineering System Solutions. As I mentioned, he's coming to us from Idaho Falls, Idaho, but they also have offices in Sacramento, California, and in Las Vegas, Nevada. Oh, they're right there on the slide, I see. And in addition to doing the mechanical and electrical, they also design the structures for buildings and kind of a one-stop shop if you want to get your building designed. Justin has a bachelor's and a master's degree from Brigham Young University in Utah, both in mechanical engineering. And with that, I will turn it over to him and let him get started.
Okay, I guess that works. Yep. Wow, it's like magic. How's everybody doing? Y'all have lunch? I gotta say y'all a lot more than I've ever said in my life. So I'm gonna try. Okay, so a couple things just so you heard. Oh, man, is this really loud?
It's not normal.
Well, that's just my normal.
Oh.
I'm loud. So down here? Okay, all right. So one thing, is it doctor? Master? Ninja? So Dr. Ross said I was from Idaho. That's with a D. It's not Iowa, and it's not Ohio. That's what everyone back here, that's what they think. Oh, I know where Ohio is. So anyways, I'm from a long ways away, but I'm excited to be here. So if you haven't QR'd in, please QR in real quick before I move to the next slide. But I'm going to ask a few questions here and there. I'd like to get everyone's response. So we'll give you just a few more seconds here. If you can't hit the QR, is it working for everybody? The QR is working? Okay. Do I need to wait? All right. I think there might be opportunity a little bit later to get you on. So, this presentation, don't be too nervous. I've been doing this presentation for a lot of years, and it's geared towards architects. I totally revamped it for you, structural engineers. Yay! All right. So if you're online, or if you want to have the AIA credit, this is an accredited class. It's an HSW class. The easiest way to do that, I think, would be to send me an email if you're an AIA member. So if you want to write that down, my email address is justin@es2eng.com at the bottom of that slide. That'll probably be the easiest way to do that. I know there's probably other ways that you've been doing the AIA accreditations, but we'll take care of all the credits. We'll get you signed up on AIA. If you're not an AIA member, don't worry about it. Okay, any questions with that? All right. Let's get rolling. So this is kind of the AIA basically saying that they don't agree with anything I'm going to talk to you about. Their little disclaimer. So today I want to talk to you a little bit about energy codes, kind of what they're doing, what they've done. As Brandon mentioned, there's a lot that's happening in the world today on energy efficiency. You know, what are we trying to do? And the energy codes are what's driving a lot of that. And so we'll focus mostly on the International Energy Conservation Code, and we'll throw a little bit of California in here as well, because you can't talk energy codes without bringing up the California Energy Code. And you'll see why in a little bit. Okay, here we go. Here's our first one. We want to see who's here. So did that come up on your, oh yeah, okay, it came up. So everyone answer those questions real quick. I want to see who's with us today. Okay. Forestry students, we got structural students. Do we have anyone but forestry or structural students? Mechanicals or electricals? Architecture, perfect. I'll be nice, I promise. Okay, so the majority, we've got students, we've got a couple professors, and an architect or two. 4. Okay, next one. Here, now I'm going to start quizzing you. Building envelope, what is it? You can see that on your phone. What does that mean? What does building envelope mean? I should hide the answers because you just look up and see, oh, what's the most popular answer? Okay, so everyone's switching down here to the bottom. Let's see. Oh, good. I don't even give you the answers yet. Good. All right, next one. According to the Department of Energy, the building envelope accounts for what percentage of the overall building primary energy consumption? Yep, the building envelope. Okay, this one's spread out a little bit better. 43 people like that number. Okay. This is the most important one in the whole presentation. Let's see. I updated this morning. I think these are the top. Most of those guys are in the top 5. All right, good. I was hoping that I'd have Clemson as the number 1 answer here. The Wyoming's not here? Yeah. I'm a little worried about you guys. Okay, good. Well, we'll see. Because I had these slides last week. I totally had to redo them today. So the top 5 is changing like crazy still. We'll see. It's been a fun year. Let's go Clemson. They'll catch up. Okay, all right. I always like to kind of start off with a little experience that I had 100 years ago. So I was brand new in the industry. I was working in Salt Lake City, Utah, and my boss had a meeting he had to go to. Well, he couldn't make it to this meeting, so he asked me if I'd go. I'm like, sure. I didn't know what was going on, so I drove up to Ogden, Utah, and I got lost and I couldn't find the meeting, and so I was 20 minutes late to this meeting. And I walk in, and there's probably 30 people sitting around this huge conference room table. And we're designing a 6-story office building, doing a design meeting. So I go and kind of sit in the corner and don't ask me any questions. And I'm sitting there, and they start going around the room talking about all the different things, and they get to structural. They're like, okay, structure, what do you got? So he's talking about all these different things, and he said, okay, I know there's a cooling tower on the roof. How big is that going to be? So everyone turns to the corner. They're like, Mike, I don't know. Oh, it's big. And they're like, well, what's it going to need for support? Do we need to have a concrete pad on the roof? And I'm like, yeah, that sounds good. Concrete pad. And so the structural, as soon as you hear concrete pad, your ears perk up, right? And they're like, well, how thick? And I'm like, 18, 24 inches. You guys all should have laughed. Because I had no idea. How much does an 18-inch concrete pad weigh? You're not putting that on your roof.
225 pounds per cubic.
Good. So anyways, I felt so stupid. The whole room laughed, like literally, like belly laughed. They're like, okay, we're not asking that kid another question. So a couple of lessons to learn there. It's okay to say, I don't know. That's something I always teach my new engineers. It's okay to say, I don't know. Let me look into that for you, right? If you're scared to say, I don't know, just say, I'll get back to you. But anyways, that was fun. So I bring that up because we'll use some nomenclature, some ideas you've never seen before, but hopefully it'll help you speak the speak, talk the talk a little bit later in your careers. Okay, so here we go. Energy codes. The top line there, building sector accounts for 76% of the electricity use in the United States. Okay, huge. That's the building sector, so commercial and residential. So of that, here on the right, 35% HVAC, 11% lighting, 18% major appliances. That's like refrigerators, those types of things. 36 is miscellaneous, like electronics. So we're going to focus quite a bit today on the number one, HVAC. And I put in parentheses building envelope because what is the HVAC really taking care of for the most part? It's usually the building envelope, right? The walls and the roof, the windows. And so we can really lower this number with a really good building envelope. Okay, we make a really energy efficient building. You're not spending as much or using as much energy on your heating and your cooling systems. So we're going to focus there. So the energy codes, that's been a big focus of the energy codes, basically back to 2000. Let's see, where did it say? It's another slide coming up. Sorry, I'm getting ahead of myself. So the energy codes have been around for a lot of years. The International Energy Conservation Code is kind of the most common across the United States. And so this is just a graphic that shows what states have adopted what version of the codes. I find this pretty interesting. If you look to the west, Oregon, Washington, Montana, they're bright green. So they've got the most stringent codes adopted. California is white just because they didn't have a real color for it. They're off the chart, and we'll talk about that. Their energy code is called Title 24, and it's way more than any of these codes. So it really should be a really bright green over there. It's not white. So South Carolina, where are you at? Not so hot, right? Not so hot. But it kind of just gives you an idea. Like, for example, Wyoming doesn't even have an energy code. They say we're not going to adopt an energy code. And so I don't know if that's specifically what all the whites do, but I know Wyoming does not have an energy code. So we're not really consistent across the United States. There's some room for improvement there. But I will mention this little caveat. On some of the things, it really doesn't matter. Like if you're going to go buy a piece of HVAC equipment, they're all building the equipment to meet California's energy code. So you kind of by default are following their code to some extent.
Are there any federal codes that govern this kind of stuff?
For the most part, it's state by state. Yeah. I think you get into the federal governance on federally owned buildings. They'll have some different applications or different requirements that they'll institute. But yeah, for the most part, it's all state adoption. Great question. So that just kind of shows where we're at across the country. This next one is the one I was thinking of. So this is what energy codes have done since 1975. Okay, there's not very many of us that were alive in 1975 in this room. But if you look at this, is kind of a cool graph. So if you look at the 100, that's kind of a normalized energy use, right? And then each code adoption, in theory, we drop the energy use down, right? We're getting more and more and more efficient as we go. So it's really interesting how we kind of, the periods of time where we just kind of flatline and we're not really doing much. And then there's times where was it? There's like a 19% drop right here to 2012. Look at those drops. So we've made a lot of progress over the years of getting our energy usage down, and it's all through the codes. Now, right here, ASHRAE, that's an HVAC association. They've got the goal to have net zero by 2030 for all commercial buildings. Who knows what net zero means? Who can explain that to me? architect. Perfect. Thank you. Excellent. So if your building is net zero, it will produce as much energy as it uses. Okay, does that make sense? So most buildings are going to use some kind of energy. And so that's where you'll produce some energy with photovoltaic. You'll do PV. Maybe you'll do some wind power to supplement that or to compensate for that. That's what net zero is. And then there's another challenge for the architects, AIA 2030. That's a carbon neutral. Okay, it's a little bit different. Their challenge is by 2030, we do not want to use any carbon-based energy sources. Okay, but both of these challenges really are driving, we want to get from here to here. Look at that line. What's going to have to happen in the codes? Right? You look at this slope. Like if you try to put a slope here, right, we're going to be net zero over here somewhere, right? So what's going to happen to these codes? Oh, you're going to see those 19% reductions time and time again. And so that's why I like to use this slide to say, okay, this is what's coming. Because it's coming. The federal government, these organizations, people are committed to getting our energy usage in our buildings down. And so there's some pretty drastic things that have to happen. So I kind of want you thinking as we kind of walk through a couple of these things, what is my role going to be in this? You're all going to have a huge role in this. And we need to think outside the box. We need to think about things differently than we ever have before. Okay, so this is just kind of to set up what we're going to spend a little bit of our time on. In the energy codes, there's a couple of ways to show that you meet the code requirements. Okay, the first is basically there's some tables. The tables will have some requirements for all your windows and walls and roof. And you say, check, check, check. We meet these requirements. It's called prescriptive. Okay, that's the first way to do that. Sometimes you can't hit the prescriptive for whatever reason. And we'll get into a couple of those in a minute. I don't want to give away one of my questions. So you really want to, you still have an efficient building, but there's just one of these items, you just can't check that box. And so one way to meet energy code requirements is you can do an energy model. Here, that number 3. And these are kind of cool. Basically, you build a model in some software and you say, okay, this is the roof, this is the wall, this is the windows, I have this many people, I have this many computers, I have this much lights, I'm going to be open from 8 to 5 every day. And anyways, and it goes through and does a simulation for the whole year on what it would cost to run and operate this building. And if that designed building is 85% of the cost of a code minimum building, then you pass energy code. So just keep that in mind. There's various ways to pass energy code, but prescriptive is usually the most common, but you can do an energy model if you're running into some issues. So here we go. This is going to set up our next segment that we'll spend most of our time on. Is it working for everybody? Okay. People are just nervous. Or maybe reading it, sorry. Which wall type has the highest overall R value? Okay, we got some honest people in the room. That's good. All right. So we're neck and neck between the 2x6 metal stud and the 8-inch CMU. We got some wood lovers in the room. You're in luck. Okay. I don't think I give the answers.
Well, you gotta tell me.
I thought I gave answers here. The answer is I don't know what R value is. That's the one I was looking for. Let's talk about, well, actually, we are going to talk about this in a minute. So it's actually the 2x4 wood stud at 16-inch on center with R11, which is crazy, isn't it? Is that intuitive? Right? You have an R19 bat. Does everyone know what I'm talking about when I say R19 or R11? Okay, I've got some other slides for that. So hold the thought. We'll talk about it. All right. What's the maximum allowed percentage of above grade walls that can be glass? So you just type in a number. Like if you think it's 80%, type in 80. If you think it's 70%, type in 70. And someone just said what I said. So the code actually says you can only have X% of your above grade walls can be glass. What do you think that percentage is? We've got some 100%. We got some architects in the room. You got some 20, look at that, 20, 100, 60. Come on, we need a lot more than this. Take some guesses. 90. I don't know how to see more. These must be our top. So most of the room thinks it's a pretty high percentage. Okay, hold that thought. We're going to get to that. Okay, let's go back to the R value then. Okay, R value. You're building a house, you've got your walls, you've got some wood studs, right? And then you put in some insulation in between those studs. That insulation is going to have an R value. A lot of times it's R11, it's R19, R20. That insulation will be different than spray-in foam insulation, right? But the R value is the measures the material or assembly's resistance to heat. Okay, so what I need you to remember today, the higher the R value, the better the wall, right? That's a really good resistance to heat. U factor, sorry, I always call it U value, so U factor is just the opposite. It measures the material's ability to transfer heat. So it's not a resistance, it's actually an ability to transfer heat. Very easy, it's 1 over R, okay? So the U factor is simply the inverse of the R value. So does that mean, is a wall, does it get better as that number gets bigger or smaller? If it's the inverse, what do you think? You want it to be small, okay? R value you want big, U value you want small, okay? Easy? All right. SHGC, this is for windows. Solar heat gain coefficient. So this is kind of cool. It basically says, all right, of all the solar energy that hits my window, how much of it gets through? And it's just a percentage. Okay, so you want that number low. Okay, makes sense? So R value high, U value low, SHGC you want low. Okay, those are all the definitions I'm going to define today, so don't worry too much. Okay, so we're going to talk about windows really first. And you guys, a lot of you haven't got into the world yet, as far as the design world and working with architects. Sorry. Architects love glass. So do we, right? Beautiful, beautiful buildings compared to that building, right? But structural engineers, for some reason, they always like to have shear walls and they always need to have moment frames. And there's all kinds of things they need. They're very needy. Structural engineers are super needy, is what I've found. Well, mechanical is the same thing. If I'm lazy, okay, I would prefer to heat and cool that building than this building. Okay, so we always have this on every project. There's always this, we want to do this, but we can't. And the next slide will tell you why. So I asked you of what percentage of the walls can be glass. And what were our answers? 80, 90, 70, right? Really high percentages. That's in California. You can do 40%.
I think that's our campus too. It's something 40% or lower on campus buildings.
Okay, so there's a campus design standard, 40%. The IECC is 30%. Okay, so it's a very low number. So remember when I talked about prescriptive, how to pass energy code, you got to check boxes. There's not a lot of buildings that have 30% glass. They're usually more. And so that's one way that you can still pass code is you can have really good walls or roof to kind of compensate for the amount of glass.
Shaded glass.
Or shaded glass. Really high performance glass. You can do overhangs. There's a lot of things you can do, But that's where the energy model comes in, because the model's really looking at how that building's going to perform. Does that make sense? So that's our glass. We're going to move from glass. We're going to go into walls. So we talked about R value, U factor. We kind of got ahead of ourselves a little bit here, but I wanted to explain what happens in a wall. So that this graphic is your standard metal stud, wood stud. It's drawn as wood, but a wood stud wall. Okay. The way heat works, heat goes from high to low, high temperature to low temperature. That's just how it works. And it's going to go through the wall in two different paths. Okay, so A2 is basically the path where the heat will come through the drywall, it'll hit your insulation, and then get into your room. Okay, that's one path. The other path is it's going to come through your wood stud, through the drywall, wood stud, drywall into the room. Okay, there's two paths there. And so this little formula or this little table shows you how to calculate what the overall R value of that wall is going to be. Does that make sense that it's not going to be R20? If that's R20 insulation, does it make sense that it's not going to be an R20 wall because some of the heat is going to bypass and come through the metal or through the wood stud? Does that make sense? Yeah. And so that's where you have to run through this little calculation. It's very simple, but we end up with an R value of 15.4 for this example. Okay, so it knocks that R value down. And so what I wanted to do, I wanted to show you what does that mean in real life. Okay, so I just ran a bunch of different framing types. So you got 2x4s, you got 2x6s, 16-inch on center framing, 24-inch on center framing, and different R values. And it was just interesting to see how things kind of played out. So if you look here at this number 1, adding studs. So if you didn't have studs in the wall, the R value would be the R value of your insulation, right? Make sense to everybody? You added studs, now all of a sudden you got a short circuit path for that heat to go. And so it reduces the overall R value by 23% for wood, and it knocks it in half for steel. Okay, huge. On average for this table, wood studs, they have 61% higher overall R value than steel. Okay, huge. And then the spacing, 24-inch on center is 6% more energy efficient than 16-inch on center for wood and 18% for steel. Okay, so what's the better material, wood or steel? Wood, without a doubt, right? The wood performs so much better. It's so much better of an insulator. And so this is something I thought would be, good to bring up. Keep this in mind when you're designing. Instead of doing the 12-inch on center studs, do you need that? Structurally, maybe. But these are things you kind of need to think through. Because a lot of times we kind of just get our blinders on and we're just thinking structural only, or I'm just thinking HVAC only. Well, it's a full building. It's a synergy of systems. And we really need to work together and figure out what's the best, assembly for this building. And so, before you add more studs, think about what it's going to do. If you're going to do steel studs, understand what it's going to do from a performance perspective. Okay, this next one, this is to introduce some other aspects of the building envelope. In the energy code, there's a map right here. I pulled this right out of the code, and it's basically climate zones, right? So depending on where you are in the country, you're going to have different requirements to meet. Okay, and that sounds a little weird, but I'll talk about that. The one thing I wanted to point out while we're all talking, you see this line? Can you guys see that white line where you're all sitting? What does it say? Warm, humid below white line. Where are you guys at right now? You're above the line. So why are you complaining about humidity? It is not humid here. It's not. Did you know that? So next summer, don't complain. It's not humid. You got to go below that line. Anyways, I thought that was so funny when I saw that line.
How old is that line?
How old?
Yeah, is that changing with climate change?
That's a good question. This is the most recent code.
Plant zones have changed.
Yeah. I haven't studied that to see what changed. So how am I supposed to answer that? I'll look into that and get back to you.
Yeah.
Yeah. So these are our climate zones. So Clemson, what climate zone are we in? 3. Okay, Idaho Falls. What climate zone? You weren't supposed to tell them. They don't even know where Idaho Falls is.
I think it's not.
Where's Idaho? Ohio is over here. Just kidding. So this is Idaho. Idaho Falls is like right in here. Okay, so 6. So we're going to do a little comparison. I thought this was kind of cool. So Clemson, you're in climate zone 3. Idaho Falls is in climate zone 6. Your average temperature for design is 95. Idaho Falls is 92. Pretty similar for cooling. Look at the heating. Your average design, well, your design temperature for heating is 24. And where I live, it's -6, 0.6. Okay, so average temperatures, they're different, right? 63 degrees here and 45 degrees up in Idaho. So let's look at this comparison real quick. So what I did is I kind of normalized to this wood framed in climate zone 6 as that's kind of my baseline, my datum point. So everything is compared to that. So if you do a metal, so that's a wood framed wall. This is right out of code. This is what code requires, these U values. So what did I tell you about U value? The lower, the better, right? So they're really pretty much the same thing. Wood, steel, you have to kind of meet that U value. Look at that mass wall. What's a mass wall? Any ideas? What would be an example of a mass wall?
Like concrete block?
So CMU, that example I had earlier where I had CMU with perlite fill, that's a mass wall. Concrete precast walls, there's a requirement for how many pounds per cubic feet, and that'll make it a mass wall. Look at that. That wall can be 57% worse than a framed wall. Why? Crazy. Okay, I'll talk about it. So go back over here to zone 3. All the walls in zone 3 can be worse, a lot worse than in zone 6. Why? If you look at this average temperature, we usually heat or cool to about 70 to 75 degrees, right? So right now we're probably 76.5. Yeah, 0.5. So the closer you are to 70s, right, you don't need to heat and cool a whole lot. So that's why your walls don't need to be as energy efficient. But over here, right, 45 degrees, that's a long ways from 75. You're going to be heating and cooling a lot. Well, heating. And so you need to have better walls, right? So this makes sense up here. I kind of have a question here at the bottom that may not make sense at all. So the SHGC, what is SHGC talking about? Windows. Yep. So that's kind of your heat transfer through the glass. Well, in the code, it says in Idaho Falls, I need an SHGC of 0.38. But in Clemson, it's only 0.25. So that means I need a that's a big difference, by the way, in real life windows. That's a huge difference. So I have to have a much better window in Clemson than I do in Idaho Falls, which is totally opposite than what we saw up here. Why? Any ideas? Okay, there's more sunlight. What does sunlight do to a building? Heats it up. What do we need in Idaho? Heat, right? That's our average temperature, 45 degrees. So they take that into account. They're like, it's probably better to let some of that heat in the building. Does that make sense? Kind of cool. Sometimes codes don't make sense. This all makes sense when you think through it. So the windows, they look at that. They look at the SHGC, and so you don't have to have as good of glass in some of these colder climates because you're actually helping the performance of the building. You're using natural heat.
So passive solar.
Passive solar, yep. You're bringing that heat in. So I thought that was interesting.
I have a question if I can.
Please, yeah, if anyone has questions too.
So we have more heating days in Clemson than cooling days.
Well, this is just a temperature.
Okay.
I would have to look up the cooling days and heating.
There's more energy spent on heating than there is in cooling here? No. More energy spent cooling than heating.
That's what would be my guess without looking it up. But we have all this data. ASHRAE collects and compiles all this data. And we actually have cooling degree days, heating degree days that'll tell you those things. But no, we do. I'm sure you're cooling here more.
I think it affects by winter sun. I mean, I think we're gonna have a lot more winter sun coming in than you do in Idaho.
Yeah, yeah. So just it's interesting when you're doing prescriptive. These are some of the things that you'll do on every single project. You know, the architect kind of takes the lead on putting those assemblies together and detailing that, but don't just close your eyes and put your blinders on. Help with that whole project team and have a synergistic system that, you know, is looking towards energy consumption of that building. Okay, remember when I talked about thermal mass, or the mass, excuse me, we talked about CMU walls. It was like 56% worse. And I'm like, why in the world, if you're going to spend the money for a CMU building, you don't have to have a very good building, right? That's kind of what that code says. Well, here's a couple of examples I want to just to kind of prove that point or kind of show that point. These are domes. Okay, there's a company by where I'm at called Dome Technology, and this is what they do. They build these domes all over the world. Most of them are industrial domes, but they kind of tinker into the commercial side. And this one on the right, your left, excuse me, it's a Montessori school. So there's two domes, and they built them, and so we're like, hey, we're going to do some cool stuff with this dome. Okay, so what we did is we didn't do any air conditioning, and we're just what's gonna happen. So let me explain. Let me back up. So these domes, the way they build them is they'll take a PVC membrane and they blow it up. They literally put a huge fan in it. It blows up like a balloon. It's super cool.
Like a plastic ring.
Yeah, and they blow that up, and then they'll come in there with urethane, and they spray 4 inches or so of urethane. That's your insulation. And then they'll come in and do shotcrete. And that's your structure. And they've got these little tabs that kind of tie it all together. And that's the dome. So when they built this one, this is their world headquarters. This was all the way to the ground, and then they came in and cut it out later. They cut these sections out. So over here, it's on a stem wall. So this is a CMU wall from here down, and then the top is a dome. So what happens with mass walls, so let's just take the school for example. This was our theory, right? Kids are going to come into school in the morning. The dome's going to be nice and cool. We cooled it off all night long. And the heat, as the kids kind of put off heat, right? We're just all little heaters. That's all we are. We're putting off heat. The lights are putting off heat. It's just going to get sucked up into that dome, into that mass, into that concrete. And by the end of the day, we'll be okay. We didn't really see a temperature rise, and then we'll just cool the dome off at night. That's thermal mass. That's why they're giving you some credit and letting you have a lower R value, if that makes sense. So that was our thought. This is going to be awesome. So basically, I designed this system so I could bring in outside air at night when it's cool, and we'd just cool down that dome. Well, what we found is we couldn't cool the dome down in one night. It was such a good thermal battery. That's really what it is. It's a thermal battery. It performed so well because the insulation's on the outside. I couldn't cool it down. And I mean, it was amazing. We had temperature sensors out here on the dome concrete, and it was crazy how well it would hold that heat. But that's the concept and the principle behind the thermal mass is you can transfer heat in and not have to really cool for a while. But then you got to get rid of that heat. I've done projects with Dome Technology where we've had they've done like auditorium additions on schools. So it's just an auditorium dome. Well, what happens at an auditorium? You have an activity or an event lasts 2 hours and then nothing for like 3 or 4 days, right? So it works great there. Basically what happens, we pack that thing full of people, it starts to collect the heat, and I don't need to run air conditioning because that dome is just sucking the heat in. And then we let 4 or 5 or 6 days go by and it'll radiate that heat off and it's ready for the next one. So that's where you can do some cool stuff with thermal batteries. This building, so we built that one first. This was their world headquarters. We learned a few things off of that one. So on this one, what we did is we put radiant tubes through the shell. And so we basically just run our well pump, because they're on a well, they're kind of out in the boonies, and we're on a well, and we just run a well pump through that skin. And so we don't have, they have air conditioning on the perimeters where there's glass, because there's just a lot of solar gains, but the whole center of that dome has no air conditioning at all. And we just run tubes, and we take the heat out through the tubes. So that works out really well. But that's the thermal mass concept. Okay, that's why you get a reduction in your requirement, because it kind of helps pull some of that heat naturally. Pat.
What do you do about air exchanges to get fresh air in?
Yeah, we still have those systems. We just don't, we're heating and cooling those systems, but not the space themselves. So we're supplying neutral air, like 70-degree air into those spaces. Yeah, great question. But this has been really cool. It's been in operation for probably 10 years, and it works great. It works really good. So these are just some things to think about as you enter the industry. There's going to be a lot that's going to happen with building envelope, right? What was the percentage? 35% of the energy that buildings use are HVAC, which a huge portion of that's going to be because of the building envelope. And so that's why I put this in here, building envelope. There's going to be a lot of innovations that are going to happen. Remember going back to that slide with our energy codes? We got to go from here to here. That means you're going to see some aggressive things happening here. And I would dare say a lot of you will be a part of that. That's pretty exciting. There's some really cool stuff that you can do with building envelope. Any questions on building envelope? Okay, the rest of this is just some kind of interesting things. We're not going to spend a whole lot of time on each one, but I thought it was interesting for you to kind of see what else is happening in some of the codes. One of the requirements in energy codes right now, you heard LEED before. LEED is a system that's been around for a lot of years, where you would get points for doing certain things. And if you got so many points, you're a LEED platinum or LEED silver, LEED gold. Well, all those LEED points have kind of worked their way into the energy code over the years. It's been interesting. Commissioning used to be a LEED point. Now it's required for every single building. And so commissioning, just to keep it in kind of your terms, it's basically all we're trying to do is make sure that the building was installed and it's operating the way it was designed. That's really all it is. A quick example on this, we did a high school auxiliary gym addition. Okay, so they built this big auxiliary gym, built a connector that tied into the existing building. Easy, right? Walk away, great. Well, during the winter, right, our minus 6.6 degree winters, I got a phone call. And I'm like, we cannot keep this connector above 30 degrees. I'm like, well, that's not good, because we have sprinklers in there. You know, the fire sprinklers, you're going to freeze and flood everything. So I went over there to try to figure out what's going on. I looked at all my calculations. I'm like, man, it should be working fine. Well, I ended up grabbing an infrared camera, and I went around and I saw some huge issues. And so I poked my head up above the ceiling, and it was so funny. I could see where the connector tied into the existing building. I could see my car through a gap in that connector. Like, it was, yeah. So what happens, these contractors, some contractors just hurry up, get the project done, and move on. And so it was just this whole thing was just wide open to the outside. And to make it worse, where they tied into the existing building, it was a big soffit that was open air. So that soffit was open to outside. So basically, I was just trying to heat outside. But that's where commissioning comes in. You try to catch some of those things along the way. So there's a building envelope commissioning that's really big right now. A lot of the commissioning does focus on mechanical, electrical, but building envelope's definitely a big one. There was another church. I got a phone call, said, hey, I can't ever turn my building down below, I think he said 70 degrees in the winter, or I start freezing stuff. I'm like, well, that's not good. And so took an IR camera, infrared camera, started looking around, and same thing. They had the attic space with holes, gaps everywhere going down into their pipe chases and things. So we went in, and well, we didn't. We had a contractor go in and just seal everything up, and boom, he could turn his building down to 60 degrees when they weren't using it. So it's a big business right now, but that's the point of commissioning, is just to make sure everything got installed correctly and it's operating the way it was intended. So this is just the commissioning process. We're not going to spend time on it, but just know that that's there. That's really, if that's something that's exciting, that's a huge market. You could spend a lot of time and energy and effort in the commissioning process. Okay, so again, a couple of things that are just kind of interesting, really. There's a demand response. So this is the California code. Their code right now today says you need to connect your building to the utility company. So they'll have a little control wire. And then you have to hook that up to your controls. And so what happens when there's a brownout condition, they just don't have enough power, they'll shut buildings down. That's there today. That's how they're dealing with some of their outages. So in your controls, you either have to just dim all your lights to a certain percent or turn some of the HVAC. In fact, it says you have to turn it up if it's in cooling or turn it down if it's in heating. Or I think there's a thing in there that says if you've got a really low productive employee, you can just shut that person down. You just have a trip on their power. Just shut. They're not doing anything anyways.
Like
Just
a movement sensor.
yeah. So anyways, that's there in California. That's coming. That's going to be a standard requirement, I think, in a lot of especially the larger cities. It's lighting and HVAC. So you have to actually. So if it's 75 degrees, they're going to make you go to 80, but it's all automatic. They send a signal, and your building has to just do it.
Presumably, they like to cycle people on and off,
Right. Yeah. So, but they can tell. Yeah, they can control that. So that's there. This is just a slide on lighting. Lighting is huge as far as what's happening. What you guys remember the percentage due to lighting? First slide, you guys remember? 11. So 11% of our building use is lighting. Well, there's been a ton of changes to lighting with LED. Okay. And I could talk forever on LED. I'm not going to. There's just a lot of stuff happening with controls and just keeping things, just to the levels they need to be. The most efficient fixture or a piece of equipment or anything is off. Okay. So that's what a lot of the controls are all supposed to do. It's just keep things turned off. Okay. This one's kind of cool. This came out a few years ago in California, and it just blew our electricians' minds, our electrical engineers. So this came from LEED. This used to be a LEED point. And I've done a lot of LEED projects, and we never, ever did this point because it was so expensive. And so they just put it in the code. And so basically right now in California, you have to make all of your electrical, are we doing okay? We're doing all right. We have to make sure all of our electrical uses are metered, meaning all the HVAC, they have to be metered. All the interior lighting have to be metered as interior lighting. So what that means is you've got an electrical panel and you pull all the power out of those panels. You guys have all seen the panels in your house with the breakers, right? Well, the easiest way to do this is to have one panel for every single one of those lines. Okay, so instead of one panel, you got what, 6? It's huge. It's just a ton of work. And so that's a requirement in California. So what you're seeing is you're getting these smart panels that are coming. They're becoming a lot more affordable. So instead of buying 6 panels and wiring it totally differently, you can wire a house or a building the way you're used to. You just use this smart panel and just say, okay, this breaker number 7 is lighting. And it'll do all that. It'll do all the math and the metering automatically. So I put this in here just to kind of show you some of these requirements that are in these codes are really pushing technology. And getting the technology to where it's affordable. LED was the exact same way. LED lighting came out, nobody put it in because it was so expensive. Now everybody has it. A lot of that's because that's really the only way to meet energy code sometimes. But a lot of these codes will really push the marketplace. So this is kind of what's coming, right? We talked about we've got to change that slope to almost a vertical slope. We got to drop if we're going to get to net zero. So building envelope we talked about. I predict there's going to be a lot of innovations over the next few years in building envelope. You're going to start at the core of a building and just look at every part and piece, and you're going to see a lot of innovation. HVAC and lighting, the technology is crazy. It's going crazy. AI in controls, you're going to see that pop up and be huge. AI is going to make it so these buildings, I think you were talking, was it this building you were talking about where it can track where people are, and like you've already got some pretty cool controls in this building. It's going to go crazy. And then watch California. I always say that. Look and see what California is doing because it's coming. They kind of test it there, and then it makes its way into our other codes. But there's a lot of things that need to happen to get that goal of net zero. And I'm sure, like I said, you're going to be a part of it. But it's exciting. There's a lot of neat things that are happening in the industry, and that's what I wanted to talk about. And I want to leave a couple minutes for questions. What do you got for questions? Go ahead. Yeah.
Building usually the foundation slab, so I think concrete slab, any kind of design out there to use as a thermal battery.
Yeah, that's a good question. So the question was about the concrete slabs and using that as a thermal battery. And yeah, there's in fact, there's a lot of kind of the magic with these domes is a lot of times the application has a raw concrete floor, and it's a lot of square footage. And that's communicating directly with the earth. And so you can store a lot of energy in those slabs. And so, yeah, I think what happens though is we put the carpet on the slab and we're insulating that slab. And so we're limiting our exposure to those slabs, but no, we can use those thermal mass properties in slabs just as easily as you can overhead. Great question. Okay, say that again. Environmental, the smart panels. It's such a good question. I don't know. So let's talk about that. So I kind of have to go back to the LEED portion of that to have it make sense. Because in the LEED portion, when this was years ago, that used to be a point. And the whole point was, and I skipped totally over this, so thanks for bringing this up. You can't improve what you don't know needs improvement, or if it's not measured. And so that's really the premise behind that is, okay, where am I spending all my energy? Is it in the HVAC? Is it in my lighting? All those categories. And so that's the point of it is once you measure it, then you'll know, okay, I'm spending way too much on my HVAC. Let's go see why. That's the point, is to kind of see all these different categories. Where's that energy being used the most so I can go and improve it? Because that's with LEED, that was the other point, is now what are you doing about it? And so that's going to come. That's going to come. There'll be a requirement in California where you're going to have to go in and improve, X percent year over year on whatever your highest energy use area is. So, does that answer that? Great question, because I did totally skip over that. Because without that, you're like, yeah, what's the point? But that's the point. They want you to measure what's going on in your building so you can go in and make improvements.
Do you think at any point, like the life cycle impact of some of these things going into construction are going to come to the code, like environmental product declaration?
Yeah, so the question was, any life cycle impacts, are that going to make it into the code? And I absolutely. I think you're going to start to see that these next few code cycles. I think that's going to be a big focus. Now, it's just me talking, But I totally think you're right. There's going to be a lot of life cycle that you'll look at. It'll all be incorporated, Pat.
So in our state, I think, y'all help me if I'm wrong, I think that our energy code is way down like 2009
Yeah.
because our state legislature will not let it go higher. And I think that's the case in other states. I've never seen a map of energy codes, but I have seen a map of building codes. And so political will to make all this happening, are you thinking there is, there's gonna need to have government to government, like federal to state, say, if you don't do something about this, you're gonna lose money or state funds, because that's how, right now, the building codes are not regulatory. They are, they're
Right.
regulatory, but they're not passed at a national
Right.
level. And I don't know what's gonna put the mode to doing this, but I know the energy codes, which is where the big problem is, are, the state is just very resistant. And
Yeah.
some states are very resistant to building codes, i.e. Mississippi and Alabama. But well,
Yeah.
that's true.
Yeah, no, it's a great question.
So what do you think about that?
Yeah, it's a great question. I from what I see and from what I've heard and read, a lot of the states that don't really have the aggressive codes, it's not that they don't want to be good stewards, right? Efficient. There's a lot of things in code that are a little bit out there, right? That probably shouldn't be there. And so that's their way of maybe weeding some of that out. And their thought process is, well, I still am going to get a really efficient piece of equipment because that's all I can buy. Or I'm still going to get, you know what I'm saying? Like, you're still going to get these other things because of these other states that are running everything. They don't feel like they need to be on the leading edge of that. But no, you're right. There's because it's a state decision. And like we showed on that map, we're varied across the United States. There is no uniformity. But I think the other part of that too is just costs. It's not free. A lot of this stuff is not free. And especially when you're living in the world we're living today, that plays into that they're trying to, right, kind of get more buildings built, and keep them as low cost as they can. But no, I think you're going to see more of that. You're going to see more mandates, more legislation, for sure. And it'll be at the federal level. It will.
I see like private sector also come into play, like Duke Energy keep sending me like free like cloud.
Yeah. Yeah.
Kind of counterintuitive, but my understanding is better for us to keep down the usage itself.
Well, that's because they can't make enough.
Yeah. They can
Yeah.
make up.
And that kind of, when we were I want to go back to a question. You talked about the building envelope and the codes, the AIA and the net zero things. Is that going not just in the building itself, but the type 3 suppliers and stuff in the LCA? So, if you are using solar panels on a building, does that mean that the solar panels also can't use fossil carbon to make it, to manufacture it, and glass?
So you're talking the AIA challenge.
Yeah.
Great question. I would have to dig into the notes.
Yeah.
My overall understanding is yes, it goes into everything.
Oh my God.
Yeah, it's huge. It's a huge undertaking. It's a huge goal. But yeah, great question. Right.
Concrete,
Yeah.
burning limestone, how are they gonna make buildings without?
Yeah, you have till 2030 to figure it out.
Oh my gosh.
That's what all these people are here for.
Oh, good luck.
No, great question.
How are you gonna build anything with a concrete building?
Right. So there's a lot here. It's easy to say, this is what we're gonna do. There's a lot that goes into it.
Wood is
So.
good. Let's just take it.
This was brought to you by Weyerhaeuser.
I know, thank you.
Let's everybody round of applause. Thanks, guys.